So we're going to look at the energetics of solution formation. So we're going to talk about this rather conceptually, so please try to stay with us here. So thinking about a solution forming, we can imagine this happening in three separate steps. So the first step might be taking that solute where the particles are together. Maybe this is sugar, it's a solid, the particles are together, and we have to get those particles apart from each other, right? So in order to do that, we have to break the intermolecular forces that are holding them together, and that requires putting energy in. So we're going to call this delta H for the solute, for pulling the solute particles about, and so that's going to be greater than 0 because we have to put energy in. We have to make an investment, okay? The next step would be looking at the solvent particles. Again, we're going to have to get these guys away from each other to make room for the solute particles. So once again, we're having to overcome the intermolecular forces, which requires putting energy in. So again, this is an endothermic process. So delta H for pulling the solvent particles apart is also a positive number. Does that make sense? When we let the solute and the solvent particles get together now, there are intermolecular forces that occur between them, right? And so the heat of mixing, of allowing these separated particles to mix together, that's going to be negative. That's going to release energy because these connections are made, right? Taking those forces apart, like you think of, two Velcro objects, or magnets might be a better analogy here. Think of, two magnets, little Brio trains or something, and you have to pull them apart because they just want to stay together, right? But this is the part where you're taking, that's not what I meant to do, where you're taking them and you're putting them together again. You're pushing those two Brio trains close to each other, and the magnets just snap them together, right? That's a release of energy, okay? So the energy change, or the enthalpy for forming that solution, is the sum of those three changes. And the overall sign is going to depend on which ones are bigger, right? So forming a solution can be exothermic or endothermic. Just depends on the relative strengths of all those intermolecular forces. So this looks like one of those Born-Haber cycle things, right? So we're starting here. Here we have our pure solvent and our pure solute. This is aggregated. I'm just distracted by this pink thing in here. I have no idea what that is. Sorry. So the steps that we talked about were first taking the solute and separating that. So that requires an input of energy. Taking the solvent, separating that requires an input of energy. And then when you put these together, that's going to release energy. So if this one is bigger than the sum of those, then the overall forming of the solution will be exothermic. Heat will be released. When the solution forms, it will get warm. This is an endothermic process where the sum of the energy needed to pull the particles apart is larger than the energy gained when you let them come together. And so as this solution forms, it's going to be endothermic. It's going to be absorbing energy and will feel cold. So those described solutions in general. Now we're going to just look at aqueous solutions. So the heat of formation for a solution is equal to the energy to take the solute particles apart, plus the energy to take the solvent particles apart, plus the energy when mixing. So what we're going to do is we're going to combine these two terms and call this the heat of hydration. So that is the enthalpy change or energy change when 1 mole of a gaseous solute is dissolved in water. So that's the heat of hydration. So we're pulling the solute particles about and then getting them into the liquid is this amount. So this is always going to be exothermic, and fairly largely exothermic, because we're forming ion dipole forces, and what we were breaking up in the water was hydrogen bonds. So the formation of the ion dipole forces is greater. So, talking about ionic compounds, delta H for that solute, the energy to take that ionic compound apart into its ions in their gas state, that is the opposite of the description of lattice energy. Lattice energy was taking ions in the gas state, separated from each other, and allowing them to come together as a solid. That was the lattice energy. Releases a lot of energy. So this heat of solute that we're talking about here is equal in magnitude to the lattice energy, but opposite in sign. It's just undoing a lattice energy. So if the delta H for the solute is a bigger number than, a smaller number than the heat of hydration, that means that the solution process is exothermic. The solution feels warm. The opposite case, we have the solution feeling cool. And so those like instant ice packs that you can get, you squish them around, there's something inside that breaks and then mixes together. So there's water in there and an ionic compound, and it's something that is an endothermic heat of solution. So when those mix, it absorbs energy and gets cold. Any questions?